of chapter 2 about Heaps generating function. So we just recall from the previous lecture a few reminding. So we remember we define the weight of a heap by you have any map which is called weight evaluation, sending the basic pieces on a ring of polynomial in variable x, y, z, etc., an integer coefficient or coefficient in a ring k. So a weight is typically a monomial, like a q, t power I, or anything like this. Then the weight of element of a heap, the weight of a piece, is the weight of the projection. So the weight does not depend of the level of the piece. And now the weight of the heap is a product of the weight of all the pieces. So it's a certain polynomial or a certain monomial in formal variable. And the first basic lemma of this course is the inversion lemma, that the generating function for all possible heaps, so I suppose it makes sense, this generating function, the sum of all the weight, which is going to be a formal power series, many variable, is going to be the inverse of this d, the denominator, and the denominator is the alternating sum of the weighted trivial heap. Trivial heap means that all pieces are at level 0. So the poset underlying the heap is empty poset. And you have a sign plus or minus 1, plus or minus 1. The number, this is the number of element of f. I call this the alternating sum of the generating function of trivial heaps. So if you want to remember this proposition in terms of picture, here is a trivial heap of pieces with a generating function d, and here is a heap with generating function 1 over d. So to making a heap is equivalent to taking the inverse of a generating function. But the most important inversion lemma for application is the extension of this inversion lemma.
So in the 1 over d, are you doing an alternating? I mean, you're changing it to being
D is alternating, yes. D is this.
Oh, that is d. Okay.
D is the denominator, the generating function of trivial heaps with alternating plus or minus. This is a d. D for denominator. Now we have an extension of this inversion lemma, which will be very useful for application in different fields, especially in physics. Is that extension, you take any subset M, any subset of the basic piece, and I am interested in the heap having this condition. If you take any maximal piece of the heap, the projection of this maximal piece is a basic piece, which must be in M. For example, a pyramid, there is only one maximal piece. If you fix the projection of this maximal piece to be somewhere on the floor, somewhere on the basic pieces, then you get as a special case of this general inversion lemma. So M can be anything. If you put M equal P, then you get back the 1 over D. But if you take M any subset of the basic piece, then the generating function is going to be a rational, not rational, if everything is finite, it will be rational, but in general it can be infinite power series. So it will be the ratio of 2 in power series, a numerator n divided by a denominator d. D is exactly the same as before. There is no change. It's the alternating sum of weighted trivial heaps. But now n is again a generating function of certain trivial heaps. Alternating generating function of certain trivial heaps is a trivial heaps such that all the pieces, every pieces of the trivial heaps does not belong to M. So trivial heaps of pieces in P minus M. Yes?
So V of the empty heap is always, it has to be 1.
1. V of the empty heap by convention is 1, yes. V of the empty heap is 1. This is very important, yes. Because when you multiply two heap by the empty heap, this is your unit element is the heap's monoid. It's equivalent to multiply by 1 in the polynomial or the power series. So if you want to have a picture in your mind to remember this theorem, here is a picture. So here I have a heap of pieces, and in blue, you see in blue, I have 3 maximal pieces, such that the projection, when you forget the level, you go to the basic piece on the floor, then the projection must be element of M. Some element of M. I don't claim that you need to have all possible elements of M. And also maybe it's some element of M can be 2 elements of M, can be in concurrency, can be independent. Of course, when you take maximal piece, each element are not independent, say they are. But maybe in M, some element can be in competition with some other element. So generating function of such heap is going to be the ratio of these 2 trivial heaps. In blue is the trivial heaps with pieces not in M. And here, all possible pieces. So the empty trivial heaps, the 1 is important because in my generating function here, it's going to be 1 plus something, and D will be 1 plus something. And last time we gave a proof of this inversion formula by taking a typical proof in so-called bijective combinatorics. It's a proof by constructing an involution, a weight preserving involution. Sometimes people call this a killing involution. So this involution is going to work on the pair of 2 elements E and F, where E is heaps with maximal piece having this condition, the projection are in M. F is a trivial heaps. And to any pair EF, I am going to associate another pair E prime, F prime. So I am going to collect them 2 by 2 so that the weight is the same. The total weight is product of all the pieces of all the both E and F, but the sign has changed. So they will cancel in this big summation. This product of this, they will cancel 2 by 2. And what remain on the right-hand side will be the element, the pair EF, I am not be able to cancel with another one. But you have to be precise when you define the pairing 2 by 2 of such a EF. So you have to define an involution, a map phi, which send EF onto E prime, F prime, and if you apply phi again, then you go back to EF. Involution is equivalent to say I'm pairing them 2 by 2, but maybe the involution is not defined everywhere. So I confess that this is not a canonical involution. There is many different ways, but you have to be very precise how you pair 2 by 2 the element so that they cancel. And n, you see, the numerator, yes, I finish, is the involution is not defined in that case on the pair where E is empty heap and F is a trivial heap with pieces in P minus M, which give you the numerator. Yes, you have a question?
So just about what we mean by maximal piece, does it mean that there's nothing above it, or does it mean...
Yes, maximal piece. There is 2 different definitions. In the definition of the Heaps monoid or commutation monoid, it means in the commutation monoid, it's letters you can put at the end of the word. So some people in trace monoid or commutation monoid, they call this the terminal alphabet. It's letters that if you move inside the word, the commutation class, you can put it at the end of the word. Which means that in terms of heaps, there exists a factorization. Your heap can be factorized into a certain heap, multiply by this maximal piece. And intuitively means that if you take the maximal piece, you can lift it above without hurting, without touching any other pieces. Or other definition, I have defined a poset associated to a heap, and the maximal piece of the poset are exactly the same maximal piece of the heap I defined before, or the terminal alphabet in terms of words and commutation monoid.
So particular maximal pieces will never have dependency.
So between 2 maximal pieces, there is no dependency, because if there is dependency, by the axiom of the heap, one would be above the other one.
So
Yes?
if you rewrote this equation as, say, 1 by n times that sum is 1 by t. So 1 by n itself would be the generating function of all heaps for the poset p minus n. Right?
1 over n, yes.
So it seems to suggest that, if you think of it as 1 over n times summation v of e.
Yes, equal 1 over d. This will be, I am going to give you, this is the second proof of the inversion formula. So students are very good in this class. They are anticipating this is another proof that we will give a general lemma on heaps, which will give this kind of identity that 1 over d equals the summation 1 over d equals summation of this multiplied by 1 over n. Well, let's go back to the end of the previous course. I'll take an abstract of. So we have seen some example, the generating function of heaps of dimers on the segment 0k, enumerated by number of dimers, and we have seen that this is the inverse of the Fibonacci polynomial. So what is Fibonacci polynomial? It's some polynomial we will meet, especially in the section with physics. There will be many polynomials like this related to Chebyshev polynomial. So Fibonacci polynomial is defined by the following. You take a graph which is a segment of length n with n vertices, and you take a matching of this graph, means you are taking a collection of edges in red which are 2 by 2 disjoint. And this polynomial, fn of x, is a generating function for all possible matching of this segment. And the weight of a matching is each dimer is counted a weight minus x. So I am counting matching of the graph segment by number of dimers with the variation that I put a -1 for each dimer. So a minus x, this means the number of edges in the matching. So here this matching would contribute to minus x power 3. So this matching will give you a term minus x power 3. And you sum over all possible matching, including the empty matching, no dimers, so this gives you 1. And if the maximum possible of dimer you can put, it depends if n is even or odd. If n is even, then every vertices will be covered. And in graph theory, they call this a perfect matching. So you see this matching is equivalent, this is the D, the denominator. Trivial is going to be trivial heaps of dimers. I am taking heaps of dimers. The dependency relation if 2 dimers have a non-empty intersection. And I'm taking heaps of such things, and this is a trivial heaps, -1, and I put a -1 for each dimer. Second example, generating function for semi-pyramid. We are in the case of the extension of the inversion lemma for a subset of maximal piece contained in M. So here the definition of semi-pyramids is pyramids of dimers on the integer positive or 0, such that the unique maximal piece must project on the segment on the dimer 0, 1. So you see here is a unique maximal piece in blue. It's touching this vertical axis. And if you look carefully in this picture, no dimers, if you try to lift the dimer, it's going to hit every other dimer, every dimer. If you look above the heap, you cannot see any dimers in full size. You see only these blue dimers. You see the two extreme, completely in full size, the 2 blue points. So this is semi-pyramid of dimer, and I apply my inversion lemma. Okay, everybody follow? The inversion lemma says that it's n divided by d. D is the same as before. And what is the numerator? It's a generating function for trivial heaps of dimers which are not in M, which means it's dimers which avoid 0. So it's a matching of a segment, but which avoids 0, so it's matching of a segment of length k instead of it being length k plus 1. K plus 1, because here my segment is of length k plus 1. I start with 0 until k equals 4. Now there is a elementary graph is a cycle. A cycle, I can take heaps of dimers on these cycles. So you see, again, I have some cycle in the same thing. The dependency relation if two dimers intersect. So I call this gamma k, the cycle of length k, cycle with k possible vertices. And again, the generating function, I claim it's 1 divided by L index k. It's a trivial ellipse of dimers which are on a cycle now. So it's matching of this cycle, matching of the graph formed by a cycle. Here is a possible matching. You put some edges in a cycle which are 2 by 2 disjoint. And this is called the Lucas polynomial. It's a generating function of such matching. It's a sum over all possible matching on the graph formed by a cycle and minus x power the number of elements of the matching. So last session I was going a little fast about matching, reciprocal of matching and relationship with Chebyshev polynomial. So I am going to repeat slowly the relationship between Lucas, Fibonacci, and Chebyshev first kind and second kind. And I will put myself in a more general setting by defining the matching polynomial of any graph, because I will use this in chapter 5. There will be a chapter about relationship between heaps and algebraic graph theory. So we'll see chromatic polynomial, matching polynomial, Riemann function for graph, etc., zeta function, or we will see many connections. In particular, the matching polynomial of a graph will be, it's a well-known object in graph theory. So I define in general a matching polynomial for any graph. So take a graph like this, and a matching, so a matching of the graph is a choice of 2 by 2 disjoint edges, like this. I have 4 edges in red. So it's kind of trivial heaps. My heap is dimers. Dimers is an edge of the graph. I can put the edges one over another when they intersect. They are common vertex, but here I have my edges. My basic pieces are edges of the graph, which are 2 by 2 disjoint. And for a matching, you put a weight. The weight of the matching. So you put -1 for each edges, and you put an x, variable x, for each isolated point. Isolated point means no edges are coming to this vertex. So here I have 4 isolated points, which give me the monomial x power 4, and I have 4 edges, which give me 1. So the weight of the matching is a product of all the variables you see on each edges. So here the weight of this matching is x power 4. And the matching polynomial is the sum, it's a polynomial, it's the sum over all matching of the graph, sum of this weight. So I have repeated here the weight. So the weight is -1 power the number of edges of the graph, x power IP of m is a number of isolated vertex of the graph. So it's a very classical notion in graph theory. It's connected to statistical physics. And there is a very nice theorem about matching polynomial of graph, which tell you for any graph, the zero of the matching polynomial are real number. So the Fibonacci, Lucas polynomial, the zero are real number, but this is true for any graph. And we will give a proof in chapter 5 of this fact using 95% of bijection, almost completely bijective proof of this fact that the zero are real number. It will be a consequence of the basic lemma. But let's go back to matching. Now this matching, I can rewrite this in equivalent way. You see, the sum of a matching, -1 power number matching, and x power number of isolated point is x power n, if n is the number of vertices of the graph, -2 twice the number of edges. Isolated point is number of vertices minus twice number of vertices which are covered by an edge. So I anticipate on chapter 5. Now we have defined last time we need the reciprocal to go back to the inversion lemma and the genetic function of trivial heaps. In fact, it's not a matching polynomial which is going to help, but the reciprocal. So what is the reciprocal of a polynomial? If I have polynomial of degree n, you replace x by 1 over x and multiply by x power n to get back a polynomial. It's just, if you look the coefficient of the polynomial from the constant term to the biggest degree, you are just reversing the way you look the polynomial. Replacing the constant by x power n and replacing the coefficient of x power n by the constant. So, so star is
Defined by the right hand.
That's called the reciprocal.
star is defined. It's by definition of the reciprocal. You replace each x by 1 over x and remultiply by x power n. So let's do it. Matching is the sum of all this weight. So it's going to be, what is the reciprocal? It's going to be the sum of the weight when I took the reciprocal. So I replace x by 1 over x, like this, and multiply by x power n to get back a polynomial. So multiply by x power n gives you this. Okay, so the weight, you see, has changed. Instead of having a weight on the isolated point, there is nobody on the isolated point, and the weight now of the dimers is x2. And so, yes?
The coefficient of the matching polynomial should count the number of matched edges in a graph, right?
Yeah, yes.
But here the coefficient is always minus 1 whole power of the number of edges. So minus 1 or 1. So how is
It's matching polynomial is minus 1. For each edges, it counts the number of matching of a graph, but minus 1 powers the number of edges. It's convenient to put a minus 1 for each edges. That's the definition of matching, and it fits very well with what we are going to do, because for generating function of trivial heaps, for the inversion theorem, we need to put a minus 1 for each basic pieces. So it corresponds exactly to it. If you don't put the minus 1 for each edges, then the theorem that the 0 are real number is no more true. So it's important to put minus 1 for each edges of the matching polynomial. And we need it for the denominator, and the graph theorists need it also for what they want to do. So the word is well done. Everybody is happy. We put a minus 1. Okay, we go. So you see, you understand the weight of the matching. I put a minus 1 for each dimer. That's the rule. The coefficient, the number of matching of the graph. Okay, A and K, the number of matching of the graph with K dimers, and you put minus 1 per K. You don't lose any information. Instead of having a polynomial with a coefficient as the number of ways to do this is, on each x power K, there is minus 1 per K. You don't, it's just a more convenient way to look at the things.
It's probably got to do with the fact that you want 1 over 1 minus.
Yeah.
1 over 1 plus.
Yeah.
You get too many negatives.
So you see, taking the reciprocal, it's equivalent to put, instead of a weight x on each isolated point, I put the weight on my dimers, which is good to apply the inversion formula. So I do inverse x into 1 over x, multiply by x power n. So you get the reciprocal, by definition, is the sum of a all matching. Now the weight of an edges is minus x2. And so the generating function for heaps of edges on a graph, I can take heaps of edges on a graph. This is more general than heaps of dimers on a segment graph or heaps of dimers on the circle, which give you Fibonacci and Lucas polynomial. But in general, generating function of heaps of a graph is the inverse of the matching polynomial. But because each dimers is weighted minus x2, you have to replace x2 by t, in fact. So this is what I was saying very quickly at the end. of last talk about for the special case of the segment and cycle graph, and to give you the relationship with Chebyshev, which are really important if you want to compute explicitly. There is many papers in physics, in statistical mechanics, where Chebyshev appears. And when you have a rational fraction, you can expand it at the sum of the power of the zero of the, and the zero is going to be cosine sinus. So you can explicitly give an explicit formula when you have a generating function, rational generating function, where the delimiter is Fibonacci because it's related to Chebyshev. This is trigonometry. So I need really to explain you this carefully because we will come back here. The third part when I will talk about the directed animal gas model, etc., etc.
What happened to the weight on the isolated edge?
There is no weight. It's one isolated point. See when I take the
Originally at x, you multiplied by
the x, you see the x is replaced. This is a matching polynomial with the weight of the matching. Now replace x by 1 over x, give you this. So this is the weight of the matching polynomial when I have replaced x by 1 over x. But it's no more a polynomial. It's a polynomial is 1 over x multiplied by x power n. Means you multiply each vertex of the graph by x. So x for 1 minus x gives you 1. So each isolated point has a weight 1, and now minus 1 will get a weight minus x2 because there is 2 vertices. So you get this weight. And if I want to work with heaps of edges on a graph, I need to replace x2 by t. So I am going to Lucas polynomial. So that was a relationship between Fibonacci and Lucas. So first Fibonacci, and then we will go to Lucas. So Fibonacci takes the graph, the segment graph, takes the matching polynomial of the segment graph. So I claim that the reciprocal of the matching polynomial of the segment graph is a Fibonacci for x replacing x by x2. So here you see on the top you have the weight of the matching, and here we have the weight of the reciprocal. And when we define Fibonacci polynomial, each dimer was weighted by minus x instead of minus x2. So this is for the Fibonacci. See how to go from the Fibonacci to reciprocal polynomial of the matching. Now what is the relationship with Chebyshev? Chebyshev second kind. It's a polynomial un given by this classical trigonometric formula. And the relationship is that un of x is a matching, is mn, the matching polynomial of the segment graph replaced by 2x.
which graph?
The segment graph, this one. So you see Fibonacci is counting matching by a number of edges, but I need the reciprocal, replacing x by x2, and then if I take the reciprocal, replacing a by 2x gives you the Chebyshev. So if you combine everything, this is the way to go from the polynomial enumerating number of ways to put dimers 2 by 2 disjoint on a segment, and this polynomial coming from trigonometry. And then it's easy to find the zero of this polynomial, so you can find the zero of this polynomial. And if I take the inverse, I will get the pole of the rational fraction, which will be important. There is some formula in physics, but the explicit formula with all the sinus, cosinus, and the zero of the Chebyshev polynomial. Now I go to the Lucas polynomial. So Lucas, the graph is a cycle graph, and I take the matching polynomial of the cycle graph, and then the reciprocal of this matching is again analog to Fibonacci, is ln of x2, the so-called Lucas polynomial. And it's beautiful that it's related to this first kind of Chebyshev. The relationship between Lucas and Chebyshev is this one. The Chebyshev is half, so it's 1 over 2, Cn, the reciprocal of the matching, and replacing again x by 2x. And Lucas, you see, relationship is here, it's x to the square. So there is different, very elementary relation between Lucas and Chebyshev, and you can easily now compute cosine of 5 theta or 10 theta by putting your edges on a circle, and you can do trigonometry without, like a kid, putting these 2 by 2 disjoint edges on a circle. Or if you put 2 by 2 edges on a segment, you get the other Chebyshev second kind. So trigonometry is easy. So this was to remind you more precisely and more generally with the matching between taking the reciprocal. And last time we have done for the segment graph, circle graph, Fibonacci, Lucas, and taking reciprocal, turning x to x2, then x to 2x, taking the graph, give you on the other way the Chebyshev first and second kind. Now we go to the proposition of our colleague, a second proof of the extension M over D, which will be useful also to see it without any involution. So the notation, I have the heap of pieces with basic piece P, the dependency relation or competition relation C script, and I take any subset M on the basic piece, and I have the following proposition, that any heap has a unique factorization in a product of two heaps, F and G. So F is a heap with maximal piece as a condition that the projection of any maximal piece belongs to M. And G is a heap with basic piece in P minus M. And I denote this, the concurrency, the dependency relation restricted to the subset of basic piece P minus M. So take a heap, take any subset M of basic piece, I have this unique factorization in F multiplied by G, with F is as a condition, the heap I want to enumerate in the extension of the inverse formula, I want to enumerate heaps having this condition maximal piece must project in M. So visual proof. Here is a heap, big heap of segment, and in purple it's a piece such that the projection go in M. You see here is M. The basic piece are many segments or real number or integer, and I have three. You see, here I have this kind of segment. Here is the floor where I project the basic piece. I have this one, this one, this one. So in the heap, you take all possible, I have put in purple, all possible segments, all possible elements of the heap, which projection go in this subset of these three. Okay, now imagine you take all the purple pieces and you push them below. You just push, which means I am taking in the poset underlying the heaps, I am taking the ideal, all the elements which are below one of this segment in purple, having the ideal generated by all these purple pieces. So the ideal in the term of heaps means you are pushing down. So here you have heaps. You see the maximal piece has the condition. The projection belongs to M. And what remains above, in green, it's a heap having no pieces at all in M. And this is a unique factorization. If you take any heaps like this in blue, any heaps in green like this, you take the product of the two heaps, you can reconstruct the separation between the two. It's just taking the ideal below or just pushing down all these purple pieces. You can, if you forget in the separation between the product, you can reconstruct. And above is any heaps of segment, no pieces are in M. So I have proved my proposition. So what is the generating function for heap? General heap is 1 over D. by the first inversion lemma in the most simple form. F, this is the generating function I want to compute. And now the generating function of this, again, I apply the simple form of the inversion formula, and I get this. This is a projection of the unique factorization in terms of generating function. And so this thing is equal to n divided by d. So this gives you, and our colleague have seen immediately this proof, second proof. So it's useful, it can be useful to think of a proof like this. Instead of doing my involution, killing involution, I can, once I have the first part of the inversion, the most simple part, then I can extend it like this. So it can be useful, and I give a complement, Lazare elimination. So when I say some part of the course are complement, means it's above, maybe it's a free course, maybe above the level of the class. Maybe I will define some, talk about words that some people don't understand, some good people or algebraists or some more advanced people will know. Just to open you a windows on something related to research or some other result. I'm not going to prove anything, just to give you an idea of the connection with other things. So what is Lazare elimination? Well, it is some paper by Duchamp and Krob in 91. Lazare is Michel Lazare. He was in the 50s. Some paper on group theory and Lie algebra in the 50s. And Lazare elimination, the idea is to apply this, what I have done before, the second proof of the inversion lemma, to the special case where M is reduced to a single letters, or a single basic piece. What happens if I have a single basic piece? And the idea is to try to decompose the commutation monoid into a product of something. Commutation monoid, in fact, is a free partially commutative monoid. The two extreme cases are the free monoid or the abelian free monoid, so it's kind of free structure. And the idea of a Lazare elimination is you have F of this, which is a free structure. It can be the free group, the free monoid, the commutation monoid, or the free Lie algebra, and you want to decompose it as something nice in a subset capital Z, and free of the structure x1, x2, xk. So you have eliminated, see, you select one of the letters, which generated your free structure, and you eliminate it, so you have again the free structure, and you have something which appears here. And you try to have something nice. And this product can be a product, semi-direct product, or anything like this. So in the particular case, for example, the free monoid, very simple example, take the free monoid, select a letter Z, and then any word can be, if you cut each time, any word can be viewed as a product of some words in x1, x2, xk multiplied by Z. So take this new alphabet, capital Z. New alphabet is any sequence of x1, xk multiplied by Z. So this alphabet Z generates a free monoid, Z star, and this is another free monoid. So you have cut your free monoid into a product of two free monoid. This one has one letter have been eliminated, and now you have a big alphabet here. Alphabet is growing, his alphabet is all these possible words. So this unique decomposition is trivial, because if you take any word, you cut each time you have a Z. So you cut, so each time between two cuts you have some word like this. And when you have no more Z, it means what remains is a word like this. So this is a very simple example of elimination of the letter Z in a free structure, which is a free monoid. And I have again now two free monoid. I can continue, eliminate one of the letters, or eliminate one of the word here. Eliminate, so, and at the end we are going to have something which can be beautiful and very useful.
This is can be used for simplifying regular expressions.
Yes, also. Yes. It's a very general principle. So the special case of the commutation monoid or the Heaps monoid, it's M equal A. This special case, then I am going to factorize the Heaps monoid in a product of two monoid, So I define Z of A, P, and is a primitive pyramid such that the unique maximal piece projects on A. Call this primitive pyramid over A. What means primitive pyramid? It's a pyramid which is not a product of two pyramids of the same kind. So primitive means if you look the maximal piece, if you look in the below the maximal piece, what I call the tube below the maximal piece, there is no other piece which project on A. Below the maximal piece, which project on the letters A, below there is no pieces which project on the letter A. Let's give an example of this. So let's say the particular case is that the Heaps monoid is a product. This is as before the product of all the heaps such that the maximal piece project on A, multiplied by the heaps which does not have as pieces A, and now I claim that this heaps of pieces which project the pyramid having A as maximal piece, there is a unique, can be factorized in a unique product of such pyramid, which I call primitive pyramids. So let's give an example. There's a unique factorization of pyramid over A into primitive pyramids over A, and the proof is the following. Here is a pyramid with the maximal piece in blue. This A is a dimer 4, 5. And here you have 3 blue dimers projecting on 4, 5. And take the lowest dimers in blue, and you push. Take the ideal, which is below this one. So now take this one and push again. So each time you see you are decomposing your pyramid into a unique product of 3 primitive pyramids. And so I get this theorem that I have the commutation monoid is going to be isomorphic to a free monoid. Now this is a free monoid, the very big alphabet. Alphabet is all the primitive pyramid, multiplied by this commutation monoid. And so you can try to iterate this kind of elimination. Here I am in commutation monoid. You can select another letters. Here I am in a free monoid. I can do the same, selecting letters, and try to apply many times this. And what we get, the idea what we get is the following idea. This is a starting point to do some beautiful things. The laser elimination was for free group or freely algebra. I go back to the example of the free monoid. And when you have this unique factorization, if you know what is the freely algebra, then the freely algebra divided by x is going to be the direct sum of these 2 freely algebra. And if you repeat elimination, you can get bases of what is called freely algebra.
Can you also say what is the meaning of
primitive? Primitive means it can be put in product. Primitive pyramid, it can be taken as a product of two other pyramids.
So with
primitive.
Maximal.
With maximal piece.
Cannot be taken.
So this one. So this pyramid. This pyramid. See this pyramid, the product of 3 primitive pyramids. See, if you take only this pyramid here, the maximal piece is this, and below, there is no other pieces which project on the same letters A. In every pyramid with maximal pieces projecting on the letter A, on the piece A, can be factorized in a product of such pyramid, which I call primitive. There is 2 definitions. Primitive means it cannot be factorized again as a product of 2 pyramids of the same kind, or else primitive means that below the unique maximal piece, there is no other piece which project on the letters A. So I finish with it just to give you an idea of this elimination in free structure by repeating your direct sum of Lie algebra, even if you don't know, maybe some people know what is a Lie algebra, some algebra is. If you repeat it many times, each Lie algebra will be generated by single letters, and then you get a basis of this free algebra. And some work have been done for the commutation monoid, the free partially commutation, by taking some bases of the free partially commutative Lie algebra. This is work by Lalonde, Duchamp, Krob, and Lalonde have done this with the heaps, which we call Lindon heaps. So this is his idea, you see, I don't go in further detail, but this gives you this elimination process, which comes from very simple idea in the heaps, give you some bases, by repeating elimination many times, give you some, even the classical bases, Lindon bases, Kirchhoff bases, or Lie algebra, can be constructed this way, by repeating and, on Lie algebra, on groups, also on free group, or also on free partially monoid, and the Lie algebra related to free partially. So don't be afraid of all this. It's just a complement. It's a window open on this. Lindon heaps, Pierre Lalonde. Elementary pyramid, yes. It's we have each one have your own favorite vocabulary, so you have to switch between elementary, primitive, or... Let's go back to the inversion lemma now. I close the windows complement about this elimination of Lazare. Let's go back to the inversion lemma. And I will finish, the second part of this lecture will be the relationship between inversion lemma and Möbius function. The inversion lemma in the most simple form, 1 over d, is nothing but the computation of the Möbius function for the monoid, for the commutation monoid. So usually Möbius function is for poset. So maybe everybody know or do not know what is Möbius. So I will recall you Möbius on a poset, Möbius on a monoid, and show you that this is equivalent. This is the same theory. So what we have done, Möbius on the commutation monoid, can be seen as a Möbius on a poset also. So Möbius, everybody know Möbius in number series, the very classical, the most classical Möbius function. In number series, you have any numbers, can be decomposed into a product of prime numbers. And the Möbius function, mu of n, is defined by this. It's a 0 if n is divisible by a square, which means that one of these integer, alpha 1 or alpha k, is bigger or equal to 2. And is minus 1 power k else, which means that in that case, all the integer alpha 1, alpha k are equal to 1. So in that case, it's minus 1, the number of prime in the prime decomposition of n. And when it's introduced this Möbius function, it's very classical that Möbius function is related to the inversion theorem in number theory. The inversion theorem is this, that suppose I have a function f defined for any numbers, and from f I can define g by taking the sum of all the f. F is a function of from a number to any ring with a unit element or any algebra. And I define a new function g by the sum of all f of d for d, all the divisor of n. Take all numbers, d, which divide n, including 1 and n. Now I claim that this relation is equivalent to this relation. This is a kind of inversion. You know f and you define g. Now if I know g, I can define f by this relation. It's the sum of all divisor, mu of d, the divisor, Möbius, g of n over d. See, and mu is defined by this relation. So this is a classical Möbius function in number theory. As soon as you have a function sum over all divisor of a certain integer, then you can inversion by the mu. And I claim that the inversion lemma we have shown in Heaps theory is an extension of this. But first,
Do we
yes?
assume G is multiplicative here? G is the function.
No, any function. No, any function. Any function. So this is a classical Möbius, and I will give you a proof of this using, as a consequence of the inversion lemma. Inversion lemma is a more general lemma for the case of the commutation monoid. So what is very classical is Möbius function in poset. It's less classical Möbius function of monoid, but let's start. It's good for your general knowing, for general culture. It's very well known, Möbius on poset. It was introduced by Giancarlo Rota in '62. In fact, it was popularized by Giancarlo Rota, Philip Hall. Many people before have done this Möbius. So Möbius in poset, let's E to be a poset with order relation, this one in brown, but a locally finite poset. Any poset which is locally finite. What means locally finite? It means that every closed interval is finite. All the Z, all the X between A and B is a finite set. There is a finite number of X between A and B. So the fundamental algebraic object is what is called the incident algebra of E. Incident algebra. You take a commutative ring, R script, with a unit element, any ring, commutative, and incident algebra is any function F which associates to two elements of the poset, a certain element of the commutative ring. And it's good to, sometimes there is no condition, but it's good to ask the two following conditions on this function. That f n x y is 0 if x is not comparable with y. So it is only defined for pair where x is less than y. And for the course, it's convenient to put this. Sometimes there is not condition like this. Sometimes people say for any x, fxx is a constant, but I put a 1, it's more convenient for the... So this is a set of functions. Now incident, it's an algebra. I can define the sum and the product of two such functions. So the sum is the sum of two functions. And the product, now this is the most important definition here. The product is a convolution product. Product f of xy, you see, you take all the z which are in the interval xy. So because it's locally finite poset, there is a finite number of z. And you take f of xz multiplied by g of zy. And you sum over all the possible z between x and y. So it's a kind of a convolution product. So this is a product on this, and this makes these two with a product by a scalar. This makes an algebra, which is called the incident algebra of the poset.
So the elements of the incidence algebra
are function f, which associate to a pair xy, any element of the algebra. This is a ring, commutative ring with a unit element. So it's any function like this, satisfying these two conditions. Usually I don't need this, but it's better to restrict function like this. Because f of two elements incomparable, you don't need, it's only for pair xy, which have with x less than y. So it's a function, so this is an algebra with this product. The most important things to remember is this. The product is like a convolution product. Now there is some special element in this poset, the Kronecker function delta, which is going to be the unit element of the poset, of the incident algebra. It's a unit element. The delta of xy is 1 if x equal y and 0 else. So you can check that it is a unit element. If you take any function f multiplied by delta, this will give you back f. just check. It's with the convolution product. Second special function is the zeta function. The zeta function of the poset, the zeta of a pair xy is 1 if x is less than y and 0 else. It's a constant function for any pair which satisfies the condition that f is defined. Any pair comparable, you get 1. And now the Möbius function of the poset, it's a function in incident algebra, by definition, is just the inverse of the zeta function. So you can lemma this inverse exists. I will give you maybe an exercise to give an explicit form of this Möbius function. So I suppose it exists, it can be proof. I will not give you the proof. And Möbius is just the inverse of a zeta function. So from this definition, I get an inversion formula in the incident algebra. So you take an element M, fixed element M. Sometimes, usually, it's a minimum element of the. If there is no minimum, so usually the poset in Rota theory, you add an extra point 0, an extra point 1 above, so that the maximum and minimum. But let's take any M in the poset. Then I define, analog to the Möbius function in number theory. Suppose I have a function f, and g is related by f by this. It's the sum of all y between m and x. M is fixed. So you can define G like this. Now there is a second relation defining f from G and using the Möbius function. And I claim, proposition, I claim that these two relations are equivalent. And the proof, if you because in this proposition, f is a function of a single variable. So I transform this into a function with two variables. M is fixed. So I can define fm of m and x. And then this relation means that gm equals the product by the convolution product by the zeta function. If it's f of m and y multiplied by zeta of xy, which is 1. So this formula gives you the product in the incident algebra with the Möbius function. And now you get the proposition that these are equivalent because of this relation. If you multiply on the right of this by mu, then you get delta and you get this formula. And conversely, this is because zeta and mu are related by this relation. So exercise, you can compute completely the Möbius function of poset by this relation. So prove that the Möbius function, the mu of xy by recurrence, if you know the mu of mu xz for all the z less than y, between x and y, then you can compute the mu of xy. Or it's not difficult exercise. So this can be proved that Möbius exists. By recurrence, you compute the Möbius. So it's not easy to compute Möbius of classical poset. There is many papers in the. So this was in the 60s. It was very fashionable at the beginning of combinatorics, especially the MIT school with Rota. There was poset, incident algebra, and a Möbius function of many things. It was the 60s, 70s. So when you were a baby or not even born. So now Möbius function in monoid. So I will extend this special case, the inversion formula, the Möbius function for the commutation monoid. This is a general case. So all this is explained in the Cartier-Fouetta book, which is in French. And there is an appendix with the Kratenthaler papers, which I encourage you to read because it's in English. It's a basic lemma on heaps. But the appendix of Fouetta on the Möbius, on monoid, Möbius on poset, which are equivalent, is not very classical, and it's in French. So now it's with a video recording, everything it can be understood in the. So let's take a monoid, and I have some condition. Monoid has a unit element, and it's a finite factorization monoid. Here I'm going to define what it means. Maybe there is a zero element, which is 0x equal x0. If there is no 0, you can always add a 0 to your monoid. And finite factorization, m plus will be the non-zero element of m. And finite factorization means that if you have any factorization of x in x1, x2, xk, in fact, it should be m plus, non-zero element. Any factorization. So if x is a product of x1, x2, xk, this is a sequence. S is a sequence of elements in the monoid, with xi are non-zero element, with xi different of 1. I will call the degree of this. So the number. So finite factorization means that there is a finite number of such factorization. So the xi are not 1. They are not 0. They are not 1. There is a finite way to factorize any x in the monoid like this. Every x in the m plus, the non-zero element, has a finite number of factorization with factor different of 1. By convention, I will say that 1 has an empty factorization of degree 0. There is no factor. The degree of the factorization is k, the number of factors of the factorization. So very, very easy exercise. There is no other factorization for 1. 1 cannot be factorized as x1 can multiply x2. Exercise, easy, very easy. Because if you have 1 equal x1, x2, then 1 equal x1, x2 to the square, equal x1, x2 to the cube, etc. So you can repeat, and you find an infinite number of factorization of 1. So 1 has no other factorization than the empty factorization. Now, analogous to Posset, I define the incident algebra of the monoid. Again, I take a ring with unit element equal to 1, and I take the function f from the monoid, non-zero element of the monoid, to the ring. All the function from the monoid to the ring are non-zero. M plus is non-zero element. Satisfying these two conditions, the sum is obvious, and the product of two functions in this incident algebra is a sum, like a convolution formula. So it's a sum of f of u g of v for all possible decomposition of x on uv, including the decomposition where u or v equal to 1.
What is M plus?
The set of elements which are non-zero. So it was m plus, non-zero element of m. Finite factorization monoid.
Wait, so 0 and 1 are different things.
Yes, it's different, yes. M has always a unit element, and maybe there is a 0, maybe not. Sometimes I need to put a 0, sometimes not.
Special symbol.
It's a special symbol, yes. 0 and 1 are special letters. For
One is
the...
sort of the empty word, but 0 is not
no, 0 is not the empty word, it's something... The killing 0 is... you destroy everything with 0, no. Usually there is no 0 in the commutation monoid, the heap monoid. The unit element, the 1 is the empty monoid, the empty heap with a weight 1, which is the 1.
distinguished.
Mhm.
So 0 is like the least element, and then you take the.
0 is like the black hole. It's It's a black hole in the. But in the heap, I have no zero in the.
Zero derivative would be zero.
Yeah.
0 into x is 0.
Yeah, yes, it's a zero.
0 into 8 is yeah, black hole. Yeah, that's right.
But empty word is one.
Yes, empty word is 1 and. Well, I follow the exposition of Fata in the appendix of Cartier-Fata, so maybe sometime you need to put a 0, sometime it depends on the monoid. But in the commutation monoid, we have never seen any 0. It was only the empty heap, which is a unit element, and which corresponds to 1.
Were we even allowing, I mean, zero could exist in computation.
It could exist, yes. So this is the incident algebra is defined by this. And we know that this is defined because there is a finite number of factorization. There's a finite number of ways to cut x into a product UV. So this is well defined. Now we define in this algebra the zeta function. It's a constant function. It's 1 for any element of the monoid. You define the analog of the Kronecker for poset. The unit element is this function. It's 1 if x equal 1, the unit element of the monoid, and 0 else. So, and this epsilon is a unit element of the incident algebra. You can check that if you multiply this by the product, the convolution product of two elements of the incident algebra of the monoid, it's a unit element. If you take epsilon times f, if you put g equal epsilon, then epsilon will be only non-zero only for v for g of v equal 1. So if you have v equal 1, then x equal u and f of u. So you see it's a unit element. So I need in this factorization, I allow u of v to be 1. And now the Möbius function is again the inverse. There exists an inverse in this incident algebra. It's the inverse of the zeta function. It exists. We will see an explicit expression. Analog to the explicit expression of Möbius for poset, there will be an explicit expression of Möbius for monoid. See, everything is similar to poset. It reminds you the poset. The zeta function, the unit element which is not the Kronecker but which is epsilon, analog of Kronecker, and now the Möbius, inverse of zeta for this unit element. Now I have the analog that there is some inversion between the relation. This relation, if I define G to be the sum of all f of v for all the factorization uv equal x, if I define the second relation that f in function of g involving the Möbius function, then I claim that these two relations are equivalent. And if you look carefully at the definition of the product, it means, in fact, that G, this relation means that G is a product of the zeta by F, and this relation means that F is a product of G by mu. And because multiplying on the left by mu about zeta, and you get epsilon. If you multiply, for example, by mu on the left here, you get mu g equal mu zeta this, which is epsilon, and epsilon f is f. So you get back this.
I didn't understand why you need the 0.
No, you don't need it. Somewhere to put the 0. Forget the 0. No, in general, it was... I told you I follow the exposition of Fata, and he said in general maybe there is a 0, maybe we need 1 0 we added, maybe there is no, so forget the 0. It's a black hole and we are stuck in the black hole, so let's take out of the black hole.
But in the commutation monoids that we're dealing with, anyway we won't...
No 0, it's not, no 0. No 0. Here I take in full generative for any monoid.
So does
the incidence algebra act on the set of all functions from the monoid to the commutative plane?
It's any function from the monoid to the algebra, to the ring R. Any function.
Yeah.
Yeah.
No, I'm saying, is there some action? This seems like the zeta acts on this and then on F. And then
Well, zeta, if you multiply by the left by zeta, yes, there is an action in the incident. You transform. NAF can be put a product by zeta, give you G. And you can go back, get back G by multiplying by Möbius. So there is an action on the left, or also say maybe action on the right. You can, what I have done on the left, I can do on the right also. So the analog relation acting on the right gives you this acting on the right, you see.
It's a bit like the group algebra.
So this is an analog of the inversion formula for Posset. In Posset I have done only in one way, but here I can go left or right. Posset also I can do left or right. You just reverse the Posset, minimum, maximum. Now how to compute the Möbius function of a monoid, how to prove the existence. Here is the following. So let's call d of x is again a function in the incident algebra. D of x, a number of factorization of the monoid M, in the monoid M. And I take d plus d as a sum of d plus d minus. D plus the number of factorization with even degree, and d minus the number of factorization with odd degree. I separate them into different, and d is the sum, of course, of these two functions, which exist because there is a finite number of factorization for any element. And by convention, d of 1 is d plus of 1. There is only one factorization, the empty factorization, with degree 0. The degree, so this is, but there is only one. So, and d minus, forget the 0 maybe. D minus, no, this is d minus d plus of 1 is 1 and 0. Now exercise, take a monoid, finite factorized monoid. First part of the exercise, prove the relation between zeta, d plus, d minus, and epsilon. Prove this relation in the incident algebra.
If you take d plus plus d minus, then still.
And from this, you deduce that mu, the Möbius function of the monoid, is d plus minus d minus. So the Möbius function is a number, total number of factorization with an even number minus number of factorization with an odd number.
Would finite factorization also imply cancelable and something?
Yeah,
Aren't you using this cancelable?
so here I don't, I'm going to need it for the next.
Could you just go back to your definition of this inversion of the F and the G?
Inversion lemma,
Yeah, the next.
That's the problem.
The next, yeah, that's the product.
next.
That's yeah. So when you wrote Gx is the sum of Fv, so you're now saying over all pairs UV such that UV
Yeah.
is expected.
Yeah.
So which means if
But I don't need to be, the monoid to be cancelable,
So just the product of zeta with
because here
meaning if the same
if I take product on the left and there is mu is the inverse of zeta and I get, but in the monoid itself there is no need to have a cancellation.
but if say the same X is say writable as some UV and U1V in some sense,
Well, you take all possible factorization.
which means you count that.
Yes, you will count. Yeah. But in fact, in the equivalence, to show the equivalence between monoid and Posset, I need to have monoid with cancellation. So this is the next section. Equivalence between Möbius function in poset and Möbius function in monoid. So take a finite factorization monoid, which is now, you say, right cancelable. If you have UV equal UW, then V equal W. So take such finite monoid, and then I am going, there exists a poset, locally finite, with incident algebra, which are isomorphic. You can find a poset with an incident algebra. The two incident algebra of the poset and the monoid are isomorphic, and the Möbius function are the same. But Möbius of the poset, there is two arguments x and y. Möbius in the monoid, there is only one argument, but the Möbius will be y divided by x, which makes sense. Y divided by x is a unique element z such that xz equal y. This element exists because of this condition. M is cancelable. So I claim that if you have this cancelable monoid, you can construct a poset E with an order relation such that yes, R of M here. Incident algebra of the poset is a isomorphic incident algebra of the monoid, and there is, roughly speaking, they have the same Möbius function. Here, Möbius of x and y will be Möbius of x divided by y.
So there's a function x comma y goes to y divided by x.
Mm-hmm. So here the construction is very simple. It's the order relation is x is less than y if and only if you see x is a divisor, left divisor of y. And then the map would send any f of the incident algebra of the poset, or f e of x and y equal f of x over y. It's a map sending the incident algebra of the monoid onto the incident algebra of the poset, and this map is isomorphic, is an isomorphism. And the poset is locally finite. If the monoid is in finite factorization, is locally finite. So you see it's you can, for a certain monoid, you just order the element to be let factor of another one. In terms of the Heaps monoid, a heap is a let factor, is a sub-heap of the other one. It's a part of the... So E is a locally finite poset. You can check proposition that there exists a unique factorization M monoid such that... and this is a reverse proposition. If you start from a poset, there is a finite monoid also with same incident algebra, with same Möbius function, same, roughly speaking, because it's function in two arguments, or function in one argument. And the construction is the following. It's you take J, all the pair start from the poset. I want to define a monoid. All the pair of elements in the poset so that x is less than y, x is different of y. I add M equal J union 0 and 1. So I put a 0 here. 0 and 1 are 0 and 1 element in this monoid I am constructing. And the product in the monoid, if you have non-zero element or different of 1, then the product, this monoid, the pair xy of element of the poset with x less than y. So product of two such pair, xy by zt, is xt if y equal x. Sorry to go a little fast because I have only 5 minutes to finish the course. So this is a product starting defined from the poset E, and then again the function from the incident algebra over here, how to define the incident algebra of the poset by this definition. F of xs and f of xy is and then you have an isomorphism, and the Möbius function of E is the same as Möbius function of the poset. Sorry to go a little fast, I want to finish with the last part is connection between, now to go back to the commutation monoid, to show that this is a Möbius function. So we have a connection with formal series. If you have a monoid with finite factorization, you can define formal power series, sum over all elements of the monoid, where the coefficient is a z, an integer. And then I claim that for any monoid M, the formal power series, the sum of all the elements of the M, is inverse of all the elements like this, with the Möbius function of the monoid. So this is a general inversion theorem that Möbius function in monoid is equivalent to take inversion of the formal sum of all the elements of the monoid. Why? Because you can rewrite this like this. The formal sum of all the elements are the formal power series multiplied by this formal sum is 1. It's because this can be translated into the product. Right? To take the product of two power series is exactly the convolution product of the monoid in the incident algebra. Product in the incident algebra is equivalent to take product of this formal power series. So this product means it's a sum of a whole pair uv equal w of this. And because zeta by mu is epsilon, I get this formula equal to 1. So you see, it's another formulation. This inversion theorem in generating functions is another formulation of Möbius function. So Möbius function for commutation monoid, this commutation monoid with alphabet A equivalent to this. The Möbius function is the commutation monoid is, for any equivalence class, is -1. The number of letters of the word if the letter commute 2 by 2, and it's 0 else. This is the inversion formula we have done with only trivial heaps or words where all the letters commute 2 by 2. And we're in the case where I put a weight in my formulation of heaps, I was putting a weight for each basic pieces, but the weight is just the letter itself. I take formal, the algebra of formal variable with alphabet itself, the alphabet which are the basic pieces. In a special case of the factorization of prime number, how to get back the Möbius function of number series. I take the alphabet A to be the set of prime numbers. Now what is an element of the commutation L of P of C, the prime numbers, where every letter commute? Any n can be factorized like this. So it's a free abelian monoid, every letter commute. And then you have the multiplicative monoid is equivalent to the free abelian monoid. In other words, any numbers, if you like picture, I like picture, I say, so all the letters commute, no pieces are independent, and any numbers n, in fact, is in bijection is a heap of ball. Each, the basic piece are prime number, and this is a decomposition of the numbers into prime numbers. And so you get classic Möbius theory that Möbius function of this abelian free monoid is trivial heaps, which means that there is, if the number is divisible by a square, it's 0, and you need all in each vertical line, at most one ball. So you get back classic Möbius in number theory, and this formula, now I finish with this, if I replace each ball the weight to be the prime number inverse of prime number power s for s any numbers, what you get is this identity. From this special case, you get this. And this is this identity, in fact, is a Dirichlet series. And you have a Dirichlet series when you have any sequence of numbers an. The famous Riemann zeta function is for an equal 1. And this identity tells you that the inverse of the Riemann function is the sum of the Möbius function of classical series, which is a special case of our inversion formula for heaps where there is no concurrence relation at all. And some people in France, in Grand Bretagne, are trying to make the analog of number theory with general heaps, with cycle on a graph. So there is a whole work progressing to have zeta function and graph and heaps of cycle. And when we will have the chapter on graph, I will say maybe some words about this zeta function and the extension of number theory to graph theory. Thank you very much.